here we are for unit number 4, all about forces. Now, it's really a continuation of unit 3 where we talked about Newton's laws. As this unit, we're going to get a little bit more in depth with specific forces. We're going to talk about gravity, we're going to talk about friction, we're going to talk about springs, and I think that's it. I think those are the only ones. I'm recording this one more in the middle of the day, so there might be a little bit more background noises. You'll hear birds, you'll hear cars driving, maybe our neighbor's kids. It's going to happen. I will try to edit as much of that out as I can, but it's probably not going to all be out. So let's dive into the first section. This one's all about Newton's universal law of gravitation. It's just all about gravity. We've learned a little bit about gravity before in the last unit, but this is going to be a little bit different. So what is the law of gravitation? We're going to talk about that and how to solve questions involving that. Gravity. Gravity is the attraction between two objects with mass. So if something has a mass, it's going to attract another object with mass. Typically, you would view this between big objects like planets, but it also occurs between two people or two objects that are really small. It still happens, it's just not as big of a force. So here's our equation for that. Fg, you've seen Fg before, but Fg is equal to capital G m1 m2 divided by r squared. Capital G is our gravitational constant, so that one never changes. It's always equal to this. That's given on your formula sheet, so you don't have to memorize it, but that one is always the same. M1 and M2, those are the masses, and then R is not the radius. R is the distance between the centers of mass. So if I've got two planets, R is the distance between the two centers. It's not to the edges, it's to the centers. So let's do some examples. So one is the force of gravity exerted on a 3 kilogram puppy that's sitting on the surface of the Earth. The radius of the Earth is this, and the mass of the Earth is this. Again, that's on the formula sheet. You don't need to have those memorized. So here's the Earth. Here's our puppy on the Earth. And the radius is from the center to the edge. So that is the center of masses. Now, technically, the center of mass should be to the center of the dog. But since the dog is, I don't know, maybe half a meter, it doesn't make as much of a difference compared to the radius of the Earth. So I'm not needing to do that extra little bit. Here's our equation. We have our numbers, plug them all in, and then we get what Fg is. Now here's why you needed to know scientific notation and why that was in the introduction unit, because you're going to have to include scientific notation and get comfortable with that. So what is the force of gravity exerted on this 3 kilogram puppy? But except now it's floating in space at an altitude. So altitude means from the surface to the object. So if we were to look at what that looks like, here's the Earth, here's our puppy. The altitude is this. Here, from the surface of the Earth to the dog, that is altitude. But that's not what the R value is. Remember, the R is from the center of mass to center of mass. So we have the center of the Earth to the edge is this. In our equation, we need the R value from the center of the Earth to the puppy. So that is what the R value is. So when I plug that into the equation, we add the two distances together for the R value, and we get this is our force of gravity. Notice it's less because the dog is further away from the planet. And that makes sense. The further away you move from the Earth, the smaller the force should be. So now we've got Superman. He weighs 500 newtons on the planet Krypton. We want to know how much would he weigh if he was at an altitude equal to the radius of Krypton. So this is a very common question. So just be prepared. This is a type of question that you will get where you are told nothing about the planet, nothing about what the actual radius is, and you are just going to need to be able to solve something like this. So it seems like you're not given enough information, but we can actually solve this. So the method for this is always going to be the same. Originally, Fg is this equation, and it equals 500 newtons. That's his original weight. That's when he's on the planet. Now his new weight, or his new force of gravity, I'm doubling the distance between Superman and the center of Krypton. He was originally at R. Imagine here's the planet. Here's Superman on the planet. R is the distance between those. Now he's doubling that. He's at an altitude that's equal to the radius. So I've doubled the distance between them. When I square that, I get a factor of 4. Now I'm going to show you one step here that might not make sense. I'm factoring out this 1 over 4. So I'm doing that to show it as something separate, Because if you notice this box here, and you notice this box here, these are the exact same equations. M1 is the mass of Krypton, M2 is the mass of Superman, or the other way, doesn't matter. That bird is really loud, I don't know if you can hear that. The R, in this case, is the same. So since up at the very top, the box is equal to 500, that must mean that the box at the bottom is also equal to 500. So all those variables times each other and divided equal 500, which means that this equation becomes 1 over 4 times 500, which that we can actually solve for. So by doubling the distance between them, I'm actually reducing the force of gravity by a quarter. So this is a common type of question. Your method for solving this will be the same. Let's do this again with a different situation. So the USS Enterprise, spaceship from Star Trek, in case you don't know, orbits a planet at some radius r. We're not told what that is, but at that radius, we are told that it weighs 2 times 10 to the 8 newtons. Then we want to know how much would it weigh if it orbits a planet that's twice as massive, but it is now at half the radius. So you can tell that this is this common question because you're only told the original weight and then something doubles or triples or halves or something like that. So again, originally, this is our weight or the FG. For the new one, I'm doubling the mass of the planet and I'm halving the radius. So I just put a 2 beside one of the masses and half by the radius. And notice with the radius, it's in the brackets, right? So the squared applies to everything in that. So I'm going to expand this out. So my 1 over 2 at the bottom, if I square it, becomes 1 over 4. Again, I'm going to factor out these numbers. So 2 divided by 1 over 4, that part separately, because this G M1 M2 over R squared, this value is the same as what we originally had. So this box equals this box. So when I plug these numbers in, I will get 2 times 10 to the 8 in brackets, and 2 divided by a quarter is just 8. You can put that in the calculator and figure that out. Multiply that, here is our new weight. So again, that's a common question. So there you go, that is the first section about gravitation. Hello everybody. So for this unit, we've got something special. So this one's gonna be a more of a kid edition that we're gonna do because we have a special guest. Hello special guest, do you wanna introduce yourself? No, she doesn't want to introduce herself. Oh, okay. Oh, well, our special guest wants to be a surprise, which we'll see if when she starts talking that you will recognize her. Okay, so same thing applies. Special guest, I'm going to play us a clip from The Incredibles, and you need to see what doesn't make sense. Okay? She's nodding her head. Perfect. Okay, special guest, what do you think? What part of that do you think was not correct?
Because he was running so fast and then he couldn't drown.
He couldn't, yeah, he was running on top of the water.
Yeah.
Do you think that's possible?
No.
That's interesting. Did you know that there's a lizard that can run on the water?
Yeah.
You know that already. Oh, perfect. See, look, he's just running and he's going really super fast. So maybe if he's super speedy, do you think maybe he could do that?
Yeah.
Maybe. He'd have to run pretty fast. But the thing is, he'd have to push down on the surface tension really lightly, but also really heavy to push himself upwards.
Yeah.
So it'd be pretty difficult.
Yeah.
And then what about this part? Watch here. See, he goes into the cave.
Yeah.
He runs on the ceiling and then turns around. Do you think that's possible?
No.
No. And then look, he comes to a stop. Oh, and he turns around. And he comes to a stop and turns around. Like he's running on water. And look, he's standing on top of the water.
That cannot happen.
He's not even falling yet.
Yeah, that's not true.
That's not true. And then after a little bit, oh, then he sinks.
That cannot be
That
true.
cannot be true. Okay, yep. Do you want to introduce who you are now? Or do you think they've figured it out?
I think they have to guess.
Oh, they have to guess. Okay, that's part of it, is you have to guess who the special guest is. Okay, so that's this video, and we will see you in the next section for a different video.